Okay, so we're going to do some actual related rate problem practice here. Um, I don't know what day you guys are going to be getting on this. I'm assuming this will probably be Wednesday this week. So I'm going to kind of put together an algorithm for solving related rates. Know that, related rates are all pretty much going to be differentiated with respect to time. So there's going to be a number of steps that we're going to follow. So step one is going to be to go ahead and we're going to draw a diagram, right? So we're going to draw a diagram of the scenario. And that's almost a necessity for many of the problems. Some of them you'll be able to do without a diagram, but diagrams are going to make things much clearer. Step two is we are going to record all of our knowns. We're going to record our givens, and we're going to kind of determine what our wants are going to be. So knowns can be dimensions, it can be speeds, it can be, all that stuff. So knowns and givens, that's kind of overlap. I don't know really why I listed them separately. And then the wants are what it is that we're after. So let's continue on. So then we're going to do step three is we're going to have to identify the formula that relates. So identify a formula that relates our givens and our wants. Okay, so in a lot of cases that's going to be pretty obvious. Sometimes we're going to use one formula to do some of our work and a secondary formula for other pieces, but examples will definitely clarify what's going on that. Step four is we are going to be very critical thinking. So we're going to identify what's static, meaning it doesn't change as time passes. So something that's static was the example that we had where Jad was in the room. It was the height of the room. Anything that doesn't progress or change as the problem continues can be identified as a static. And why it's important to know if it's a static is if something's a static, it means that we can substitute in a value right away, because if it's static, its rate of change with respect to time is going to be zero. So, in theory, you don't have to substitute right away, but it makes our differentiation life dramatically easier. So we're going to identify what's static or unchanging and what's dynamic, right? And so dynamic means as the problem continues and progresses on, does that value change? So, in that last problem we had, it started at 6 meters was the length of the room. After 2 seconds, it's down to 3 meters. If we let it progress again, that length is going to be different. So we're going to identify what's static and what's dynamic. And that's really, really important, because what we're going to do then is we are going to substitute any static values immediately. And that's not because it's a necessity, it's just because it simplifies our life a lot. So this simplifies the problem. Okay, so that's what that does. It's going to simplify the problem a bunch. And then step 4, or 5, because I can count. Step 5 is going to be, we are going to differentiate with respect to time. Now I'm going to put in time. I suppose that it's feasible. We might be able to come up with examples where time isn't what you're going to differentiate with respect to, but by and large, time is what it is that we're going to be differentiating with respect to. I did a great job over here. Nice. So differentiate with respect to time. Then, after we've differentiated with respect to time, step 6 is we're going to be able to now substitute any, I'm going to put in quotes here, snapshot values. Okay, and what I mean by snapshot values are the things that, I might have said when the room was 3 meters long. So when the room was 3 meters long, it meant, that wasn't a static value. It was something that if the problem progressed, it would be different. But because we've differentiated, we're taking a snapshot in time, we can substitute that snapshot value in. And then, it doesn't really need to be a separate step, but, and then step 7 would be, of course, to solve for what we're after. So solve for what we are interested in. Okay, so that's sort of our cookbook. So if we go back and get our diagram, we're going to record our knowns and our wants, or you can call them givens, I don't really care. Step 3 is going to be identify the formula that relates our givens and our wants. Sometimes it's more than one formula, but again, examples will make that clear. Step 3, that was 3. Step 4 is going to be identify what's static and what's dynamic. Again, it's really, really important. If you know that something is static, substitute right away. It makes differentiation dramatically easier. Step 5, then, after we've done our substitutions, is we're going to differentiate with respect to time. And then step 6 is going to be substitute any snapshot values that we have. And step 7 is going to be solve for what we're interested in. Okay, so we're going to work through a couple of examples. So I'll work through one example, and then and you can either pause right away after I've described the problem if you think that you know how to go to it. Otherwise, listen through it. But then the subsequent problems, I really do think it'd be wise for you to, just like in class, kind of invest the time. That's where we get the knowledge is to actually stop and invest. So let's look at a fairly classic, and really there's only so many variants that we're going to explore in high school when it comes to related rates. So let's go with example. We'll make it fun. We'll make it example 1. So imagine that we had, so a really classic one is if you have an elevator. So sometimes they're called gravel elevators. That's like, it's a beauty. And if you've ever driven past an aggregate, like a pit, sometimes it'll be screening sand or screening gravel. And this is an elevator that, goes this direction, it turns around, and gravel goes winging off like this. And it ends up forming on the ground a fairly conical pile. You can imagine that this is going to go like this. And so what we've got here is we've got a conical pile of gravel, right? And so what we have here is a conical pile of gravel, all this gravel. And so some of the things that we're going to know, okay, let's say that the gravel is being poured at, so gravel is accumulating at a rate of, how about, I don't know, 20 cubic meters per minute. Okay. And what we're going to say is when the pile is, 10 meters in diameter, at what rate is the height of the pile changing? And there's some other information that I'm going to provide to you. I'm going to tell you that the ratio of the height to the diameter, okay, so we've got a height and we've got a diameter. I'm going to tell you that when the pile, let's make it fairly simple, when the pile is, 6 meters tall, it is 5 meters in diameter. And so that's going to be a constant ratio, that it's always going to be in this proportion of 6 height to 5 diameter. All right, so if we kind of consider our strategy here, what we're going to have to do is, okay, I've got this diagram, it's a thing of beauty. Next thing I want to do is I want to record the givens. So here are some givens. Well, we know that it is a, let's say that was not very nice. Let's change this to 4 just to make our life easier. Make the numbers a little bit nicer. So I'm going to say that the diameter to the height is given as 4 to 6, and we'll revisit that in a bit. We are given that the gravel is accumulating at 20 cubic meters per minute. So that actually pans out as being dV by dt. dV by dt is going to be 20 meters cubed per minute, and that's really important. And we have a snapshot. So our snapshot says is when the diameter is equal to 10 meters. And again, that's really important. What we want, okay, our wants are, it says, at what rate is the height of the pile changing, right? And so what we want then is we want dH by dt, and you can even put a qualifier in there when the diameter, or I'm going to switch it up a little bit, I'm going to say when the radius is 5 meters. Okay, so we've got all these things. So now, knowing our formulas is going to be useful to us. I can tell you that the volume formula for a cone, I think we should all know this, is going to be pi r squared h. That's if it was a cylinder, but it's not a cylinder, it's going to be a cone. So then we're going to divide it by 3. So there's our volume. So we know what dV by dt is, and what we really want is dH by dt. But we've got R's and we've got H's. Now, particularly now that we know how to do implicit differentiation, we know how to get this in terms of one variable. We know how to differentiate this with 2 separate variables, but it would be in our interest to try and get it in terms of one variable. And so this is where we have this whole thing that says, all right, we've got the ratio that says the diameter to the height is 4 to 6. That means that if we think about radius to height, it would be 2 to 6. That means that height, if we think about that, is equal to 3 radiuses. Now, we want dH by dt. So if I were to substitute h equals 3r in here, let's look and see what that would be. If I did that, we could say that volume is equal to pi r squared times 3r divided by 3. And so that would be 3 pi r cubed over 3. Well, that's interesting. So it's just going to be pi r cubed. Now, this is absolutely true. That is exactly what the volume is when it's given in this particular ratio. But the problem is, if you can imagine here, is that if I differentiate this right away, I'm going to have a dV by dt, and I'm going to have a dr by dt. Well, we know what dV by dt is. It's a given. Here it is up here. But then we'd also have a dr by dt. And what we want is a dH by dt. So all is not lost. I'm going to leave this one for the time being, and I'm going to come back to it in a minute. But what that really indicates to us is that because we want things in terms of h, because I wanted to know what rate is the height changing, I'm going to switch this ratio around a little bit, and I'm going to say, oh, that means that r radius is equal to the height divided by 3. So I can go back to my formula again and say, okay, well, it's going to be volume is equal to pi, and I'm going to substitute in for r. So r is going to be pi, or h, excuse me, by 3. So pi r squared h over 3. I'm going to simplify that a little bit. So we're going to have then that's going to be pi, and I guess it would be h cubed. So it's going to be pi by 9 h cubed over 3, which ends up just being pi h cubed over 27. So this is still an expression for volume. All right, so it's not as elegant, it's not as nice an expression as this one over here. Probably easier to write it as this. So volume is equal to pi by 27 h cubed. But it's still a pretty reasonable expression. So here's my expression. Now, if we go back and we think, so I've chosen my formula. I'm going to get it in terms of one variable if possible, but it's not always going to be possible. And then I have to think about what's static and what's dynamic. Well, neither the height nor the volume nor the radius are static in this case. So there's not going to be any substitutions. We're going to have to differentiate right away. So if I take this expression, I'm going to drag it over here, and I'm going to say I'm going to differentiate. So we're going to have dv by dt is equal to pi by 9, because the 3 is going to come down and cancel out, h squared, and then a dh by dt. So this is what we're actually interested in, right? dh by dt, which is lovely. dv by dt, we know that dv by dt was given, and it was given as 20 cubic meters per minute. So I can come down here and I can substitute. I can say, all right, well, the dv by dt is going to be 20, and it's positive because the volume is increasing, is going to be equal to pi by 9. Now the height, it tells us when the pile is 10 meters in diameter, what is the height going to be? Well, we have an expression for height in terms of radius. So if it's 10 meters in diameter, we can take this expression right here, and we know that h is equal to 3r. Well, if it's 10 meters in diameter, that means that it's 5 meters in radius. So I can go back here and we can say h is going to be 3 times 5. So the height is 15. So I can take that back into here and say, okay, this is going to be 15 squared dh by dt. So I'm going to multiply both sides by 9 just to clean this up a little bit. So this is going to be 180. I'll make it explicit, I guess. So times 9, and I'm going to take this expression here and multiply by 9. This is going to go with that. I'm going to divide both sides by pi. So it's going to be 180 over pi. And then I'm going to have to divide by 15 squared, which is 225. So I'm going to divide by 225 pi. And that is dh by dt. And so I know that can simplify a little bit, but I'm not going to bother doing that in my head. So dh by dt. So what that is that's telling us that the height of the pile, the cone of gravel, as it were, is increasing at 180 by 225 pi meters per second, or meters per minute. Meters per minute? I think meters per minute. Yeah, meters per minute. Okay, so I would actually then have to do a statement. I would say the height of the pile is increasing. And again, we have to make sure that we always choose the right word, because we always want to phrase it as the positive. So the height of the pile is increasing at a rate of, and then I would expect you to simplify the fraction. I just don't have a calculator handy. 180 over 225 pi meters per second when the pile has a diameter of 10 meters. Okay, and there it is. So we worked that thing out in its entirety. Now, I want to go back and I want to revisit this piece here. So let's think about what we did. We're really interested in finding what dh by dt is. But we accidentally, or not really accidentally, but naively, I suppose is more appropriate, we naively substituted and got it in terms of r's when we really, really wanted it in terms of h's. All is not lost. Okay, so if we get to this point on a test and we're like, oh crap, that's not really what I wanted, look what we can do. We can still take that. So what I'm going to do is I'm going to move this down here just so I can have a little bit more room to work with. So volume is going to be equal to pi r cubed. And I'm still going to differentiate, right? So if I differentiate here, we're going to have dv by dt is equal to 3 pi r squared dr by dt. Now, I don't really want dr by dt. I really want dh by dt. But if I solve for dr by dt, that's actually a good step for us to do. So dv by dt, we still know is, I think, what was it, 20? Yep, 20. So dv by dt is going to be 20 still, is equal to 3 pi. Well, we had a snapshot when the diameter was 10 meters. Well, in this case, we've got r. So I'm going to say if the diameter is 10, that means the radius is 5 dr by dt. So simplify that a little bit. So we're going to get 20 equals 25 times 3 is 75. So 75 pi is equal to times dr by dt. Times dr by dt. It's going to divide both sides by 75 pi. Divide by 75 pi. Those guys are going to go away. And so we know that dr by dt is equal to 20 over 75 pi. Okay, well, that's good, but we didn't ask for dr by dt, we asked for dh by dt. But look what we've got. We have this relationship from earlier on. We know that h is equal to 3r in this particular scenario. So look what we can do. We can say, all right, well, there it is. I know that h is equal to 3r, and I have dr by dt, but I want dh by dt. So look what I can do. I can differentiate this expression. So dh by dt is going to equal 3 dr by dt, which isn't surprising that because it's a constrained ratio that the rate of change of the height is triple that of what the radius is. And so I know now dr by dt. dr by dt is 20 over 75 pi. So this is going to be 30, what am I doing? Not 30. 3 times 20 over 75 pi, which is going to be, goodness, that reduces nicely, I guess, doesn't it? But anyways, 60 over 75 pi. So 60/75ths, well, look at that. We can actually see that those are equivalent ratios, as they should be, because we did the same problem, but we came at it a different way. So the point of that particular exercise was to see that even if you simplify and you get the expression in the wrong variable, it doesn't mean that we have to throw the baby out with the bathwater. We can keep on going with that by using another expression, differentiating and substituting. Seems pretty overwhelming, so I should probably simplify this just to be responsible. So divide top and bottom by 5. I think, what is that? It's going to be 12 over 15 pi, which reduces again. Divide the top and bottom by like 3, and it's going to be 4/5 pi, so 0.8. And it's the same as that expression right there. So we would then do this similar. Careful, I got my pi in the wrong spot, don't I? There we go. We would do the same type of statement here that would say, by the way, this is what our the height is changing at. So that's a pretty classic problem. And what we're going to do is we're going to try a couple more like that. So I'm going to grab me another new sheet here. So file, new. Yeah, I do want to save it. What do I want to save it as? Put that on my desktop with like a billion other things. Desktop. I'm going to save that as related rates examples. There we go. Here comes another one. So let's try another problem very similarly, but this time, hopefully, you can try and figure out what to do after I've posed it to you. So what are we up to? We're up to example. Should we bother Curtis? I better not. He get upset. So example 2. So imagine that what we're going to do here is we are inflating a spherical balloon at a rate of, I don't know, how about 30 cubic centimeters per, actually let's do it per second. What rate, we'll do an easy one to begin with, is the radius changing at when the, I don't know, we could go with diameter is 40 centimeters. Okay, and I'll give you some formulas that you might find of use. So the volume of a sphere is equal to 4/3 pi r cubed. Okay, so that's really all you should need to start this problem. So I would suggest you pause it right now and give it a whirl, and then come back when you're done. Well, welcome back. So I'm going to go ahead and solve this. So we're going to start by doing our diagram. So there's a lovely sphere. And we know that the volume is changing at 30 centimeters per cubic centimeters per second. So let's go ahead and we're going to talk about our givens. So we're given the formula. So we know the formula. That's super relevant because we're going to have to use it. And we're given that dV by dt is equal to 30 centimeters cubed per second. Lovely. So are we given anything else? Yeah, we're given a snapshot of 40. So when the diameter is equal to 40 centimeters. And our wants, what our wants are, in this case, what we're looking for is we want dr by dt, okay? So we've already got our formula that relates the quantities. Here it is right here. This one's pretty straightforward. We're going to go ahead and we are going to differentiate this right off the bat. So we're going to say then dV by dt is going to be equal to 4 pi r squared dr by dt. And while we aren't explicitly given the radius, we're really close, because if we have that the diameter is 40, we also know then that the radius is 20. So I know dV by dt is 30, so I can substitute that in right away. So that's going to be 30 is equal to 4 pi times 20 squared dr by dt. And so that's going to be 30 is equal to 20 squared is 400 times 4 is 1600. So that's going to be 1600 pi dr by dt. And then I'm going to solve. I'm going to go ahead and I'm going to divide both sides by 1600 pi, divide by 1600 pi, go away, and we're going to get dr by dt is whatever this is when you simplify it. So 16, so it's going to be, I guess, 3 over 160 pi. So what that means is the rate of change of the radius is increasing by 3 over 160 pi centimeters per second at that particular juncture. So we would need to state that. So we would say, therefore, the radius is, and it's increasing in this case, increasing at a rate of 3 by 160 pi centimeters per second when the diameter is whatever it was, 40 centimeters. Okay, so pretty straightforward. Let's adapt this problem, and we're going to keep everything the same. So it's going to still inflate at 30 centimeters per second. And we still want to know when the diameter is 40. But imagine that we changed it up just a little bit, and instead of saying what rate is the radius changing at, what happens if I had have said at what rate is the, make it pretty simple still, what rate is the diameter changing? So I could, do a part B to this problem. At what rate, well, that E is kind of long enough. Anyways, at what rate is the diameter changing? Now, I mean, I would give this to you probably as the question right off the bat, and hopefully you would recognize you could do one of two things. You could either say, all right, well, we know that diameter is double the radius, and we could have then solved for r in terms of d. So we could have rearranged it, and we could have said r is equal to d over 2, and substituted that into our volume equals 4/3 pi r cubed formula. And that wouldn't be wrong. Like, that would absolutely work. We could have worked it all the way through and been there. However, radius is pretty nice to work with because we've been working with radius since, I don't know, grade 9, grade 8. And so I probably would have solved the problem in the exact same way, knowing that I have this relationship to fall back on. And then I'd take this relationship and I would say d diameter by dt is equal to 2 dr by dt. And then I can just take this and substitute that in, right? We can just say, oh, I know what dr by dt is. It's going to be 3 over 160 pi. And so that simplifies to be 3 over 80 pi, right? So that one's pretty trivial. But imagine that we wanted something a little bit more sophisticated, but with the same type of problem. So imagine instead that I said, okay, how about part C, I guess we're up to. What rate is the surface area changing at? Right, so that becomes a much more challenging problem. So if this was a scaffolded question and we got to here, well, we already know what dr by dt is, right? We found that dr by dt was equal to 3 over 160 pi, which is all good. And then we would have to then also know something about the surface area. Well, for those of you who don't recall, the surface area is 4 pi r squared. And it says at what rate is the surface area changing? So what we want here is going to be dSA by dt, right? Well, again, we've got this lovely expression right here now. So we can say, oh, I can just differentiate this immediately because I've got this in terms of radius. So dSA by dt is going to be equal to 8 pi r dr by dt. And we know what the radius is, although I don't recall exactly at this juncture. We're given the diameter is 40, so the radius is going to be 20, so I can substitute that 20 in right away. Where did that come from? Interesting. So we can put that substitute that 20 in right away. And dr by dt we have is right here, so we can substitute that in as well. It's going to be 3 over 160 pi. Oh, isn't this going to come out as a thing of beauty? dSA by dt is equal to, and so I can actually simplify. Well, look at 8 times 20 is 160, so the 160 is going to go away, and the pi are going to go away, and so the surface area is gorgeously going to be changing at 3 centimeters squared per second at that particular juncture. Okay, so dSA by dt is equal to that. So we would be, therefore, the surface area is increasing at a rate of 3 centimeters squared per second. Okay, and so that's a pretty elegant, pretty clean solution to that. Okay, so how about we do another problem here? What would be a good one? How about imagine the following. So what are we up to? Example 3. Okay, so example 3. Imagine that we had, okay, how about a roll of super hot commodity toilet paper is being depleted at a rate of, I don't know what's reasonable, how about 1.5 centimeters cubed per minute. At what rate is the radius changing given the dimensions as outlined below. Okay, and so here we go. We've got a toilet paper. We're going to assume that this is a magical toilet paper that has no hole in the middle. It's just a solid toilet paper. The height of this roll of toilet paper is going to be 14 centimeters. And at this particular juncture, the diameter, this is one of the mega rolls, coveted 16 centimeters. Okay, so I know all of that information. I'm going to give you some formulas that you might need to know. So I can tell you that the volume of a cylinder is equal to pi r squared h. So go ahead and pause the video right now and see if you can work this out. All right, welcome back. So what we've got here is we've got this roll of toilet paper. It's being depleted at this. So let's work our way through here. So we are given, what are we given? Well, we're given that dV by dt is equal to 1.5 centimeters cubed per minute. Now, got to be really, really careful here. It's being depleted. It's going down, right? So it's going downwards. So I very explicitly need to include that as being negative because it's getting smaller. Okay, we're given that the diameter is 16. Alternatively, we could say, oh, the radius at this particular time is going to be 8 centimeters. And we're going to give that the height is equal to 14 centimeters. So we've got our formula that is relating all these things. Oh, and I'm going to list out what the find is and what our want is. So our want is we want, what do I want? At what rate is the radius? So I want to know what is dr by dt. Okay, there's my formula. Now, I'm going to go back and I'm going to be really, really critical here. In theory, I could differentiate this right away, and it wouldn't be all that bad. We'd be pretty good at it. We could say there's part 1 and there's part 2. But we always have to lend a critical thought to exactly what's going on. And in this case, the height is static. As we would pull toilet paper off of this thing, you know, the width, kind of if we thought about it on its side, like toilet paper typically is, it's not going to change. It's going to be 14 as it continues. So that is a static value. So that's really important. This is static. So I can take that 14 and I can substitute it in. And so I can say, oh, you know what? This is actually 14 pi r squared. And I can get rid of the h entirely because that 14 is static. And all of a sudden, my differentiation is going to be much more trivial. So I know then that dV by dt is going to be, I guess, 28 pi r dr by dt. Okay, and I know what dV by dt is. It is negative 1.5 is equal to, put my decimal place in there, 28 pi r. Oh, well, now wait a second. When we're going to go, this is our snapshot, so I can actually put in my radius. My radius is going to be exactly 8, I guess, dr by dt. And then we can solve. So that's going to be 160 and 64 is 224. So I'm going to divide both sides by 224 pi. So we're going to have negative 1.5 over 224 pi is equal to dr by dt. But that's horrible. We don't want a decimal mixed in there. So I'm going to multiply the top and bottom by 2. So I'm going to multiply this by 2 and multiply this by 2 just to make it a little bit more elegant. So it's going to be negative 3 over, I guess, 448 pi, no, 12, 16, no, so that's not divisible by 3, is equal to dr by dt. And so there it is, but we always have to have our sentence, so we would have to be really careful. So this is negative, which means it's decreasing. So again, I don't want to say decreasing by negative whatever. I want to actually say it's just decreasing. So we would say the radius is decreasing. I'm running out of space. At 3 over 448 pi centimeters per minute. Okay, and there it is. So I'm going to put up a couple questions onto Google Classroom as well. It has been a treat, ladies and gentlemen.